Good morning, everybody. This is Math 0310. Today's February 27th, and so I have a few announcements here to get the class started. First of all, good morning, Taylor.
Good morning.
First of all, WebAssign homework is due March the 4th, and so there's two assignments. 9.1, 9.2, and 9.3 is one assignment. 9.4 is another assignment, so you have two assignments due on March the 4th. So kind of keep track of WebAssign homework. By the way, speaking of WebAssign, there was some, you should be aware in the square root, these sections on square roots, that WebAssign will count an answer like this as incorrect. And so it'll take -1 times the square root of 7. Let's say that the answer, let's say you're looking at this problem, 5 times the square root of 7 minus 6 times the square root of 7, right? And when you know, those are like radicals, right? So you can subtract them. And so you take 5 minus 6 and you get -1. And so, you know, that would be negative square root of 7. If you write -1 square root of 7, WebAssign will count this wrong. So counts this incorrect. And counts this one as correct. Now, this actually is somewhat controversial. I complained to WebAssign about it, and they actually responded back and said, "Nope, sorry, you're wrong. We're right," which I think is wrong, by the way, and I've discussed this with numerous faculty members, and it seems like that there should be nothing wrong with -1 times the square root of 7 instead of negative square root of 7. So I just wanted to remind you of that as you're doing your WebAssign homework on this chapter, if that kind of answer comes up, make sure you write it this way instead of the -1 times the square root of 7. On the other hand, on an exam, if you ever write -1 times the square root of 7, or if you write 1x somewhere, or if you write x over 1 somewhere, I am absolutely not going to count that wrong. That's ridiculous. There's nothing wrong with any of those kinds of expressions, and so I just kind of wanted to point that out and remind all of you guys, both of you, those of you who are with me live today, and those of you who are watching the recorded video, I'm not going to be picky about that kind of thing at all when you're writing your answers out. So I wanted to point that out. Online office hours, I try to remind you of these frequently. Tuesday, Wednesday, Thursday, 11 to noon, and then Tuesday and Sunday evenings from 8:30 to 9:30 p.m. Exam 2 review, a couple of us were talking about this before I started the recording. The Exam 2 review will be posted next week. And so that will be, somewhere around the 7th of March, the 8th of March, somewhere in there. And the Exam 2 window opens March 22nd, I believe. Let me check that one more. Yeah, March the 22nd, and it runs through March the 27th. Now, I know that sounds like a long way away, but that's going to come up pretty quickly. And remember, one of those weeks in between now and then is spring break. And so it'll go pretty fast, because spring break always goes fast, you know that. So be looking for the Exam 2 review. The good news is the Exam 2 review will be up, a good 2 weeks before you take Exam 2. So that's good because it'll give you some time to do some prep work before Exam 2. All right, so what we're going to do today, our mission is to look at section 9.6 in your textbook, which is on solving equations with square root expressions. So the first thing I want to do is I want to go through some reminders before we actually talk about square root equations. So first of all, reminders. Remember that if you have the square root of Bob squared, like that, or if you have the square root of Bob squared, where the square is underneath the radical like that, regardless of whether it's outside or inside the radical. And if Bob is a positive expression, which we're kind of assuming is going to be true generally for these kinds of problems, then remember, then both of these are just equal to Bob. Right? So that when you square square root, if the expression underneath the radical is positive, then you're just going to get the expression that's underneath the square root. In that case, when the expression is positive, the square root process and the squaring process are inverses of each other. That's the way the college algebra student would refer to it. And it's kind of like they undo each other. And then another example of that, another way that you might see that written is the square root of Bob times the square root of Bob. Remember that the square is, again, as long as Bob is positive, if you take the square root of Bob times the square root of Bob, you just get Bob. Right? So some examples here for that kind of thing. For all of those kinds of problems. So if you have the square root of 3x plus 1, and that is squared, square root of 3x plus 1 squared, that would be 3x plus 1. Right? Again, remember, we're assuming that 3x plus 1 represents a positive expression. If you have the square root of 83 squared, right, where notice the 83 squared is actually underneath the radical, that doesn't matter. That's fine. 83 is positive. The square root of 83 squared is 83. And finally, if you have the square root of 5x times the square root of 5x, right? That's the example of the last one there. As long as 5x is positive, then the square root of 5x times the square root of 5x is 5x, right? So I wanted to remind you of some of that kind of thing. Also, something else. Remember that, and we use this with radicals a lot, that when you multiply conjugate expressions together, a plus b times a minus b. This is something we talked about last time in class. So multiplying conjugates, that's always equal to a squared minus b squared. Right? And that comes up frequently when you're talking about square roots. So that if you have the square root of 6 minus the square root of 3 times the square root of 6 plus the square root of 3, right? That's an example of conjugate expressions. And so that when you multiply conjugate expressions together, you always just get a square minus a square, right? So you write down that pattern, a square minus a square, and then you just fill in the pattern with the numbers that you're talking about for the particular multiplication problem. So this would be the square root of 6 squared minus the square root of 3 squared. And then you use what I just wrote down at the top of the screen there, and you get 6 minus 3, or 3. Right? So the square root of 6 minus the square root of 3 times the square root of 6 plus the square root of 3, it just gives you 3 as an answer. Don't forget that when you multiply conjugates together where there's square roots in the conjugates, you always get an answer that doesn't have any square roots in it. And so that comes up for us when we're rationalizing denominators, right? So rationalize when you have an addition or a subtraction problem in the denominator. So if you have 2 over the square root of x, let's say, minus the square root of 5, right? And you want to rationalize this, what do? You multiply by conjugates. Multiply by the conjugate of the denominator. And remember, you have to do that in both the top and the bottom. So you have the square root, multiply the top and the bottom by the square root of x plus the square root of 5, and the square root of x plus the square root of 5, like that. Right, so this is where conjugates comes up for us as algebra students, is when we're rationalizing the denominator of an expression that has an addition or subtraction problem like this. And so what happens, the denominator has conjugates in it, and so when you multiply, right, in the denominator, you're just going to get a square minus a square, right, because you're multiplying a plus b times a minus b. And so that's the square root of x squared there and the square root of 5 squared there. In the numerator, I just leave that alone. Right, just write it as 2 times the square root of x plus the square root of 5. Uh, if there was a FOIL method in the numerator, you'd probably multiply it out. In this case, I just leave it factored. And so you have 2 times the square root of x plus the square root of 5. And in the denominator, what happens? The square root of x squared is x. See the top of the screen, right? That's when you square a square root like that, as long as the expression is positive, you get what's underneath the radical. So you just get x minus 5. And what have we done here? We've rationalized the denominator. That was our starting expression in the box, and that was our finishing expression at the end, and it no longer has square roots in the denominator, so we've rationalized it. We certainly, by the way, have not simplified it. In fact, the expression that we ended up with is more complicated than the first one. So I never say that we simplify when we're talking about rationalizing, but we have rationalized it, and that can be important to an algebra student and to a calculus student to be able to rationalize an expression. Frequently, the rationalized form is something that's easier for them to work with. And so it's going to be common for you to do that if you go on to take other classes. All right, so I wanted to talk about multiplying conjugates and reminding you of that. Let me kind of highlight that that's what we were doing there. All right, and then the last thing I want to remind you of is squaring, addition, and subtraction problems. Something else we talked about last time. And there's a pattern here that's useful when you have square roots. So we're talking about taking a plus b and squaring it, and a minus b and squaring it. Right? That's, you're squaring an addition problem, you're squaring a subtraction problem. And remember, the pattern is a squared plus 2ab plus b squared, and a squared minus 2ab plus b squared. And the way I write this, with square roots, it's useful to write it just with parentheses. So I write it with, instead of the a's and the b's, I just use open sets of parentheses to kind of write out the pattern for each of these. And this is going to be helpful when you deal with square root expressions, to think about that pattern like that. And in fact, for today, that's going to be big time for us, is to know this pattern here. All right, so if we had something like this, the square root of x plus the square root of 7, quantity squared, right? This is, first of all, please, this is not equal to x plus 7. You can't just square each of these terms like that. That's not how you square an addition or subtraction problem. Instead, what do? You use the pattern that we talked about at the top of the page. So this is something squared plus 2 times something plus something squared, like that. Right? Don't write it out. Don't just square each term, because that's not what's going on there. And then what do? You fill in these parentheses with the terms that you've got for the particular square problem that you're looking at. So let's see, this is going to be the square root of x here, the square root of x here, and then 7, and then 7, like that. I'm sorry, square root of 7, and then the square root of 7, like that. Right, and just fill them in, and then do the arithmetic from there. So the square root of x squared would be x. The second term, the 2, there's nothing I can do with the 2 and the 2 square roots, because one of them is a square root and one of them is not. But I can multiply the 2 square roots together, so you get the square root of 7x. And then finally, the last term is the square root of 7 squared, which is just 7. Now, sometimes you get a radical in your answer, sometimes you don't. It just depends on the problem. But there's the multiplied expression, right? So this was our original problem. We squared that expression. When we square it, that's what we get right there. Really looks different. All right, let's do another one like that. Let's do something that might look a little bit more complicated. The square root of x minus 5, let's say plus, let's do minus 8. And we're squaring that. Square root of x minus 5 and then minus 8. Quantity squared. It's a subtraction problem. You're squaring it. It doesn't matter that the square root of x minus 5 looks a little bit more complicated. This is still the same pattern. Write this out. Write these parentheses out. I tell you, it's gonna go a lot better for you in these problems today if you'll write this pattern out when it happens, when you're squaring an addition or subtraction problem. And so then what do you do here? You just fill in these parentheses with the terms that are inside, right? So this is the square root of x minus 5 goes in here. Square root of x minus 5 goes in here. 8 goes in here. 8 goes in here. Don't worry about it being negative 8. We've taken care of the sign, right? When this is subtraction, this term right here is subtraction. Everything else is positive here. All right, so then we multiply that out, right? You square the square root of x minus 5, and that just gives you x minus 5. In the next term, the two factors that I can multiply are the 2 and the 8. So that's minus 16 times the square root of x minus 5. And then the last term is 64. And then if there are any like terms, add them together. Remember the 5 and the 16, I can't mess with those because the 16 is connected to that square root of x minus 5 by multiplication. So I can't do anything with addition and subtraction in that 16 because I'd be violating order of operations if I did that. And so I just combine the negative 5 and the 64, which gives me 59. So you have x plus 59, and it doesn't matter what order you write these terms in here. And then minus 16 square root of x minus 5. And I know at the end it sure looks tempting to take the 15 minus, or the 59 minus 16 and subtract them, but that's not possible because of order of operations. So don't do that at the end. All right, so that's the just kind of a quick rundown of some multiplication and reviewing some things about multiplication. And you'll see why I did that as we go through problems today. So now we're talking about, this is our main goal for the day, solving equations that contain square root expressions. All right, so we are going to start with some simple problems, but by the time we're done, we're going to be looking at some problems that are pretty messy. So let's see how this works. So I am going to work some problems actually that are just out of your textbook. This is section 9.6, page 1088. And so I'm going to start off with some relatively straightforward problems here. So this is problem number 394. You have the square root of 7z plus 15 equals 6. All right, a relatively simple equation, but what has it got? It's got a square root expression in it. That's the kind of problem we're talking about today. Our goal, if you're going to solve this, the goal is to eliminate all radical expressions. You need to try to rewrite this expression by eliminating all the radicals. So eliminating all square roots. Now the way you do that, generally the idea here is to square both sides of the equation to get rid of the radical, because I'm trying to get rid of the square root of 7z plus 15. And I can do that if I square that side of the equation, right? Because if I square that side, then what I end up with is just 7z plus 15, based on what we were just talking about, again, with multiplication, right? When you have a square root that you're squaring, you end up with what's underneath, as long as the expression underneath is positive. So the idea is, when are you allowed to do that? When can you just square one side of the equation? Well, you've got to also square the other side of the equation, right? Based on what you've known as an algebra student for a long time, within your solving an equation, as long as you do the same thing to both sides of the equation, you're generally okay. Now, there is an issue here with this. An issue that did not come up like when you add or subtract the same number on both sides. So we do need to talk about this for a second before I finish this problem. There is an issue with squaring both sides of an equation. So in other words, you can't just do that without even thinking about it like you do with addition or subtraction or multiplication or division. There actually can be problems with doing that. Now let me kind of show you how this is working here. I'm going to put a vertical dashed line here to kind of separate the page here. If you add the same number to both sides, like to an equation, so this is apart from the problem we're talking about right here. And I'm going to start with a super easy equation, like if we had x plus 6 equals 10. Super easy equation to solve. Most of you can just look at that and tell me what the solution is, right? That the solution to that equation is 4. So now let's go ahead and add a number to both sides of the equation. And I'm just taking a number completely out of thin air here. I don't care what I add. If I just add 8 to both sides, right? I added the same number to both sides of the equation. I have changed the equation. This is now a different looking equation. It's x plus 14 equals 18. But the deal is, even though I have a different equation, what did I not change? I didn't change the solution to the equation. The solution to the equation is still 4, right? And so you know as an algebra student that that's a legal thing to do, right? Quote unquote legal thing to do, that when you have an equation, that it's always okay to add the same number to both sides of the equation, that the resulting equation, even though it looks different, it always has the same solution as the first one, that you don't change the answer to the equation when you do that. So addition, adding to both sides does not change the solution. And the deal is that that same rule works for multiplication, subtraction, division, right? That as long as you subtract the same number on both sides, or multiply the same number on both sides, or divide the same number on both sides, as long as it's not 0, that's legal to do, right? So it works for not just addition, but for subtraction, for multiplication, and division. As long as you do the same thing to both sides of the equation, you don't change the solution to the equation, right? Does not change the solution. But now look what happens here. If I square both sides of an equation, and so let's just take a simple equation, a really simple equation here. Let's take x equals 6. Now the solution to x equals 6 is 6. Pretty tough, right? That's a tough one to solve. So the solution to x equals 6, that equation is 6. Now I'm going to square both sides. And so when I square both sides, I get x squared equals 36. And the problem with x squared equals 36, when I squared both sides of the equation, is that the solution set is now different. 6 is still a solution to that equation, but negative 6 is also a solution. And so squaring both sides produced an extra solution. A solution that was not a solution to the original equation. That absolutely cannot happen when you have addition, subtraction, multiplication, or division. If you do that to both sides of the equation, you never produce an equation that has an extra solution. But squaring both sides can, it doesn't have to, by the way, but can produce an extra solution. And so the extra solution, if it happens, has a name. It's called an extraneous solution. So a solution that's an extra solution is called an extraneous solution. And the only way to find those extraneous solutions is that you have to check your solutions. So the moral to the story here with square root equations is you must check all solutions to make sure they are not extraneous or extra solutions. All extraneous solutions have to be thrown out of the solution set, right? Because they're not really solutions to the original equation. So what I was trying to show you off to the side is that what you know as an algebra student is still good, right? You can add, subtract, multiply, and divide on both sides of an equation, and you don't change the solution. That's no big deal. And squaring both sides is also okay to do, but you have to realize that it can produce a problem later on in the solution to your equation, right? And so whenever you see yourself squaring both sides, and that's what I'm doing right here in this step in our problem, then I have to make a mental note when I do that. Hey, I've got to check these solutions at the end to see if I get any extraneous solutions to this equation, right? You have to check your solutions. So right here, I would note you must check your solution. All right, so now I just proceed on with the problem. I have squared both sides of the equation, and I achieved the goal that I set out at the beginning. What that goal was, eliminate all square roots. And now I have an equation that has no square root expression. And so now I just solve this equation, and I get 7z equals, I subtract 15 from both sides. We know that's legal to do. So I get 7z equals 21. I divide by 7, I get z equals 3. Then I get a solution of 3. Now I don't go right to the set braces and write out the solution set yet. Now what I do is I check z equals 3. And so I take my original equation, the square root of 7z plus 15 equals 6, and I put 3 in place of z. And a lot of times you can check these in your head. The arithmetic, a lot of times, will go pretty straightforward. So you get square root of 21 plus 15 is supposed to equal 6. And sometimes I put a question mark over the equal sign because I'm trying to see if these are actually true, equal. So you get the square root of 36 equals 6, and you get 6 equals 6. It certainly checks. Right? And so 3 is the solution to this equation. Right? And that's my solution set. All right, so again, the moral to the story is to eliminate the radicals, you're going to square both sides of the equation. But but when you do that, you can sometimes introduce extra solutions that are not really solutions to the original equation, and so you have to check to see if that happens. All right, so something definitely to kind of note in the problem. All right. So for those of you who are with me live, obviously shout out if you have a question, but I'm not hearing anything, so I'm assuming I'm good right now. Okay, so this is number 404. You have the square root of 2u minus 3 plus 2 is equal to 0. All right, so on this problem, before squaring both sides of the equation, make sure one radical is by itself. In other words, isolated. You'll see that word frequently used. And so you'll frequently see isolate the radical. So don't square both sides of the equation until the radical is actually on one side of the equation sitting there by itself, which it's not, notice, in this problem. So the first thing I'm going to do is I'm going to subtract 2 from both sides to isolate the radical. Right? And then that gives me the square root of 2u minus 3 equals negative 2. And now I could square both sides of the equation. So I'm going to write that out as a separate step. Sometimes students don't do that, but I want to make sure that you can look back at this to see what's going on. So now I square both sides to eliminate the radical. And on the left side, I have the square root of Bob squared, right? So you're left with Bob, 2u minus 3. And then on the right side, I'd get 4. All the radicals are gone, but I've squared both sides, so I make a mental note, I've got to check my solutions. Right, so at that step right there, I say check solutions. And so then you add 3 to both sides to solve the equation. You divide by 2, and you get u equals 7/2. And so now we're going to check 7/2. And I know it's a fraction, but you can do this. So check x equals 7/2. So I go to my equation, and in place of u, I put 7/2. And the arithmetic's not going to be bad here at all because you get canceling here. So you get the 2's divide out. So you have the square root of 7 minus 3 plus 2 equals 0. So you get the square root of 4 plus 2 equals 0. And notice here you get 2 plus 2 equals 0, which is not true. 4 is not equal to 0. And so notice that it does not check, right? 7/2 does not check. 7/2 is extraneous. And because 7/2 did not check this solution, because it was an extra solution, that means the solution set in this problem is no solution, right? You could either put an empty set of braces, or you can write no solution out in words. I would be okay with it either way. And so here is our first example of an equation that had an extraneous solution. Now, in this particular problem, you really could have told this was going to happen at the very beginning, because right here, you've got the square root equals a negative number. And the square root cannot equal a negative number, because that's when you write that radical symbol there, that square root symbol, remember that's defined to be the positive square root of a number. So square root has got to be positive when you use a radical symbol like that. So you could have, if you knew that and you were paying attention, when you saw the square root of 2u minus 3 equals negative 2, you could have stopped right there and wrote no solution, because there's no way that's going to possibly work out. All right. So next problem. Like I said, stop me if you have a question about something. So let's look at next problem I want to do is number 408B. This is number 408B. And the equation is, and this one's going to be a little bit more complicated now. This is going to be the square root of x plus 1 minus x plus 1 equals 0. All right, so we're going to solve this equation. We're going to eliminate a radical. But don't forget, you must have the radical be by itself, right? And so you've got to isolate the radical in this equation. So that's our first step. Isolate the square root expression. So that means in this problem, what I need to do is I need to move this x over. So I'm going to add x to both sides of the equation. And I need to move the 1 over. So I need to subtract 1 from both sides. Okay, and so when I do that, I will have the square root of x plus 1 be by itself now. On the left side of the equation, the negative x is gone, the positive 1 is gone, and I've moved those terms to the other side of the equation using addition and subtraction. And so I've got x minus 1 on the other side of the equation. All right, and so now I'm ready to square both sides of the equation. All right, so I've got one of the radical isolated. I write the equation down again, and I'm going to square both sides now to get rid of that radical. So the square root of x plus 1 squared, that's x plus 1, equals. Now here, please be careful, x minus 1 squared. What are you doing there? You're squaring a subtraction problem. Remember what I talked about. a few screens ago and what we talked about in class last time. When you square an addition or subtraction problem, you're talking about these patterns here. And so you're not just squaring each term individually and going on from there, right? So write this pattern down. In this case, this is a subtraction problem. We're squaring. And so this is the pattern you get when you do that. Right? And so you're going to have an x here in the first set of parentheses, another x, and then a 1, and then a 1. So you have x plus 1 equals x squared minus 2x plus 1. Now notice that this equation is quadratic. And so we're going to have to get 0 on one side of the equation to solve this. All right, so that's okay. We can do that. Right, we go ahead and subtract x from both sides. Subtract x, subtract 1 from both sides, and get 0 on one side of the equation. Remember, as soon as you see it's quadratic, you've got to get 0 on one side. So you get 0 equals x squared minus 3x, and then the 1's add to give 0. Right. Remember, when you see that it's quadratic, you have to set equal to 0 to solve it. And then you factor the other side. So you have 0 equals x squared minus 3x. You factor the right side of the equation, and you get x times x minus 3. There's just a common factor of x. You set each factor equal to 0, and you end up with 0 as a solution, and you end up with 3 as a solution. All right, and then don't forget that what you've got to do here at the end is you need to check both x equals 0 and x equals 3 to see which ones of these work out. So I'm going to kind of put this check in a different color so it stands out. So let's see. Let's check x equals 0, and it's got to be in the original equation. So you have the square root of 0 plus 1 minus 0 plus 1 is supposed to be equal to 0. So you get 1 plus 1 equals 0 or 2 equals 0. No, it doesn't check. And then I'm going to check x equals 3. So that, I'm going to kind of squeeze this in. So 3 plus 1 is 4. So you get the square root of 4 minus 3 plus 1 is supposed to equal 0. So you get 2 minus 3 plus 1 equals 0. And that does check. You do get 0 equals 0 because you get negative 1 plus 1 is 0. So what happens? 0 is extraneous, right? That does not check, but 3 does check. And so we throw out 0, and the solution set to this equation is just going to be 3. So I put 3 down, and I put braces around it. That's my solution set for this equation. 0 is not a solution, it's extraneous. Right? Frequently going to happen, does not, by the way, does not always happen when you have a quadratic equation at the end. But a lot of times when you get two solutions, you're going to find that one of them doesn't check when you look for an extraneous solution at the end of the problem. All right, so that one may be a little bit more involved because of the way the problem worked out. So let's look at, let's look at problem number 414. You have 2 times the square root of 8r plus 1 minus 8 equals 2. Now this one's actually going to end up not being as hard as the last one. When we solve it. All right, so what do we do here? First thing we do is isolate the radical, right? We have to isolate. So I'm going to go ahead and add 8 to both sides. So you get 2 times the square root of 8r plus 1 equals 10. And then I would really like to get rid of that 2 in the front also. So I'll go ahead and divide both sides by 2. And that would give me the square root of 8r plus 1 equals 5. All right, I would rather get the radical completely by itself like that before I square both sides. And so now square both sides of the equation. So I always write it down again and then square in this next step. So when you square the square root of 8r plus 1, you get 8r plus 1. And when you square 5, you get 25. Radical is now gone, so now you solve the equation. That's a linear equation in this case. You have 8r equals 24, because you subtract 1, and then divide by 8, you get r is equal to 3. All right, and so what do we need to do? We need to check r equals 3. Is that possibly an extraneous solution? So every place I see a r in the equation, I substitute 3. It's only one place. So you have 2 times the square root of 24 plus 1 minus 8 is supposed to equal 2. Square root of 24 plus 1 is the square root of 25. And so that gives us 2 times 5 minus 8 equals 2. 10 minus 8 equals 2. And sure enough, you get 2 equals 2. Yeah. And so r equals 3 is a solution to this equation. All right, that's our solution set. So I just wanted to point out a problem where you had to do some division to go ahead and solve the equation. All right, so next problem. This one's going to be more involved. This is going to take more room to go through this problem. This is number 422 in your book. Because the reason why this one's going to be more involved, I'm going to put this way over on the left side here, is that notice this equation has 2 radicals in it. Yuck. And because it has 2 radicals, it's going to be more involved as far as solving the equation. Now remember, the idea is to isolate a radical, but the square root of u plus 4 is isolated. Right? It is by itself. And even though this one had 2 square roots, you can't isolate both of them in this case. So you isolate one of them, and that one's already isolated. So I'm ready to square both sides of this equation just like it is. I don't need to move any terms around here because one of the radicals was already by itself. So I square both sides of the equation. Now on the right side of the equation, all you're doing is squaring that square root. You get what's underneath the square root, right? The square root of Bob squared is Bob. But the left side is a problem where I am squaring an addition problem. And so here is our pattern that we need to write down to square this out, right? A big difference between those two sides of the equation. On the right side, all I'm doing is squaring a single square root, so you get what's underneath that radical. On the left side, I'm actually squaring an addition problem, and so I have to use this pattern to multiply this out. And I just fill in the terms, right? So the square root of u goes into the first 2 sets of parentheses, and 1 goes into the second two sets of parentheses. So when you square this out, you get u plus 2 times the square root of u plus 1 equals u plus 4. And so I squared both sides of the equation. Remember, the goal is to eliminate a radical, or eliminate all the radicals. The problem is I still have a radical expression. We still have a radical expression, a square root. So you know what has to happen? We have to isolate and square again. In other words, you have to go through this process twice in a problem like this. Yuck. So what I've got to do is I've got to, and I'm going to write this equation down again right here. I've got to get this square root by itself. And so what I'm going to do is I'm going to subtract u from both sides, get rid of the u, and I'm going to subtract 1 from both sides. And so on the left side of the equal sign, all you're left with is 2 times the square root of u. And then on the right side of the equal sign, the good news there is that the u's subtracted to give 0, and so you're just left with 3. So it ended up being a pretty nice little equation at the end. It's not going to be too bad to solve that equation. Now, okay, so we divide both sides by 2, and now we finally have the radical isolated a second time. And so now we go ahead and square both sides a second time. So we square again, and so we get u equals 9/4. Now 9/4 is a little bit yuckier to check in the original equations, but you can. You have the square root of 9/4 plus 1. The 1, remember, is not underneath the radical, equals the square root of 9/4 plus 4. All right, so on the right side, or I'm sorry, on the left side of the equation, that's 3/2. The square root of 9/4 is 3/2 plus 1. 1 is 2/2, right? And so you get 5/2 when you add those together. Right, or you could look at it this way, that 3/2 is 1.5. 1.5 plus 1 is 2.5, and 2.5 is 5/2. All right, so do you get 5/2 on the other side of the equation? Well, you get the square root of 9/4 plus 16/4, getting a common denominator there. And sure enough, that's the square root of 25/4, and that is 5/2. That's going to check. And so 9/4 is a solution to this equation, as it turns out. Sometimes the check can be harder almost than the original problem, because you've got fraction arithmetic sometimes that you have to deal with in the problem. All right, so a little bit more involved on that problem, because you had to isolate the radical and square both sides twice in the problem. So it's a little bit yucky because of that. All right, so, but we're actually closing in on being finished with this material, which is good. Because this is about as difficult as we're going to get. So this is number 422B, and this is definitely as difficult as a problem as we're going to see. You have the square root of n minus 5 plus 4 equals the square root of 3n plus 7. Okay, so we're going to go through the steps and walk through the steps one more time for solving this kind of an equation. Now remember that you are isolating one radical. So notice that the square root on the right side is already isolated. It's already by itself. And so I am ready to square both sides of the equation just like it is. So I'm going to write the equation down again, but now I'm going to show that I'm squaring both sides. So on the left side, I'm squaring that entire expression. You put parentheses around the entire side of the equation, which means you're squaring an addition problem. And then you're squaring just a single radical on the other side. Clean this up just a little bit there. Okay. So you square both sides of the equation. On the right side, this is just 3n plus 7, right? The square root of Bob squared is Bob. But on the left side, I am squaring an addition problem. Squaring an addition problem. And so because I'm doing that, I must use this pattern to go ahead and write out the square here. So it's something squared plus 2 times something plus something squared, like that, right? And I'm going to fill in those parentheses with the terms that I've got. So the first one is the square root of n minus 5 squared plus 2 times the square root of n minus 5 times 4, and then finally plus 4 squared equals 3n plus 7. So this one's going to be a little bit yucky at the end here. So go ahead and do all the arithmetic. So the square root of n minus 5 squared, that's the square root of Bob squared, that's n minus 5. The middle one, now look, the only two things that the 2 and the 4 are not under the radical, and so I can multiply those together to get 8, but the square root of n minus 5 just comes down like it is. Because it's under a radical, I can't multiply it by the 2 and the 4. And then plus 16 equals 3n plus 7. So this is going to be pretty gross here. Let's see, so you've got some like terms here. The negative 5 and the positive 16 is going to be plus 11. So you have n plus 11 plus 8 times the square root of n minus 5 equals 3n plus 7. And now I isolate and square again. Isolate the square root and square again, because I still have a square root in the equation. So I get the 8 times the square root of n minus 5 by itself, and so that means what I'm doing here is I'm subtracting n from both sides. So subtract n there and subtract n there. Right, so that would give me 2n on the right side of the equation. And then I need to subtract 11 from both sides of the equation. So subtract 11 there, subtract 11 there. And so that gives me minus 4. Now, at this point, one thing I do notice is that every term has a common factor of 2. So at the very least, I can divide out a 2 here. I can divide a 2 out here and divide every term by 2. And so that makes the numbers a little bit smaller. So you have 4 times the square root of n minus 5 equals n minus 2. In this problem, to be honest, I probably wouldn't divide both sides by 4 to get rid of the 4. I'd just leave the 4 where it is, and I'd square both sides with the 4 sitting there like that. That's okay to do if it's multiplication. Oh, so this problem is really going to end up being a lengthy problem. This is kind of gross here. So on the left side, 4 squared is 16. This is just a multiplication problem, so you're squaring each factor. That's okay to do. It's not an addition or subtraction problem. So it's not that pattern that we've been talking about. You just square each factor individually. On the right side, this is the pattern, and you end up with n squared minus 4n plus 4. Whoa. So this equation is quadratic, and this is, this is going to turns out to be a pretty nasty problem, definitely. And you're trying to set it equal to 0. So all the little pieces on this problem are the same as the easier problems. It's just that there's a lot of things to do in this problem kind of combined. All right, so we need to get 0 on one side. So I subtract 16n from both sides. And I need to add 80 to both sides. So when I do that, I end up with 0 equals n squared minus 20n plus 84. And then you're trying to factor that equation. And let's see. How would that factor here? And obviously go back through and make sure that I didn't make any arithmetic mistakes anywhere in the problem. And because I'm looking through it right now, and I'm a little bit worried that this thing is not factorable, and that maybe we've run across one that's not factorable, which is not really a kind of problem that I wanted to look at. So I've going back through right now and actually checking through my work to make sure that I didn't make any mistakes anywhere in here. And as I'm running through each step, so that's why I'm kind of pausing here a little bit, just to go back through and make sure that I haven't done anything crazy. And so those of you who are with me live right now, if you're not completely overwhelmed by this process, you should be going through and seeing if you see anything that I did that was wrong anywhere. But I, as of right now, have not seen a mistake anywhere. Okay, so let's see, what are the factors of 84? The factors of 84 are 1 and 84, 2 and 42, 3 and, 3 and
28.
28, thank you. Yes, thank you, thank you. 4 and 21. See, and this is not factorable because those are the only factors of 84. Or maybe
6 and 14.
There you go. Okay, I'm saved. Woo, I for some reason was not coming up with 6 and 14 at all in my head. So now I feel better. Okay, so this is n minus 6 times n minus 14. It does factor. Woo. And so then you get n minus 6 equals 0 and n minus 14 equals 0. So, Raina, I think you were the one that helped me with that. I appreciate that. So you end up with 6 and 14 as solutions here. And now remember, you are still not done here until you've actually checked this out, checked the solutions to see if this actually makes sense. So if either of these are extraneous. So when you check n equals 6, I'm just going to walk through this and kind of streamline the process. You get the square root of 1 plus 4 equals the square root of 25. And so you do get 1 plus 4 equals 5. And so n equals 6 checks. N equals 14, you get the square root of 9 plus 4 equals the square root. Let's see, so 3 times 14, that's 42 plus 7 is 49. So that's the square root of 49. So you get 3 plus 4 equals 7. And that one checks also, as it turns out. And so in this case, neither of those is extraneous. And so you end up with 6 and 14 as solutions. So just because you get 2 solutions doesn't mean one of them has to be extraneous at all. So, all right, now this is among the most difficult and lengthy problems we work all semester long, by the way, this kind of problem. And you may see a couple of things here. You may see a problem like this on WebAssign somewhere, but on an exam, I'm not going to give you anything that's going to be quite this gross, just so you know. This is worse than any problem you would see on a test, for sure, which hopefully is good news for you. All right, so we will, this just about finishes up what we're going to do today then with square roots. And so we have on Thursday of this week, we're going to look at sections 9.7 and 9.8 and finish up by looking at higher order radicals. So on Thursday, to kind of look ahead, we're looking at higher order radicals, which means we are going to be looking at cube roots and fourth roots and fifth roots and so on like that, not just square roots anymore. And then we're also going to look at exponents again, and believe it or not, these things are connected. Exponents and higher order radicals are connected to each other, and so we're going to talk about the connection between exponents and radicals next time. In particular, we're going to look at exponents that are fractions. What does it mean to take something and raise it to the 3/4 power or the 2/3 power, something like that? All right, and then next week, I want to point out that we will cover a section next week that is out of a different textbook. The section that we're going to look at next Tuesday is out of the intermediate algebra textbook, and which OpenStax book. And so you do have a link to that on my Google site and in your syllabus, and so you can pull that section out. And if I can, I'll probably try to pull that section out myself. And create one separate document and email that to everybody. That way you actually have that kind of pulled out as a separate section that you can use maybe easier than having to go get it out of the textbook yourself. So I'll try to be doing that before next week. So that's just a couple of sections, one next week, and then we'll do that again a couple of other times later in the semester. So, all right. So your 9.6 homework out of the textbook, this is practice, but sure would be good if you could be looking at these problems. This is on page 1088 of your book. This is problems 393 through 425 odds. So those would be great practice problems there. Do any of you that are with me live right now, do you have any questions for me? Y'all were pretty quiet today. Anybody have any questions?
No questions.
All right. Then if there are no questions, I told you that today's lecture would probably be a little bit shorter because we had just this one topic to cover. So we've done a good job with that. So